Alright, time for another draftphysics.com video presentation. So, following up on the problem of another experiment seems to indicate that momentum isn't conserved and isn't conserved. I mean, that's all you need to say, really. I mean, that's, to me, a dramatic statement that momentum isn't conserved. So, the simple argument would be is if I did have a spring on a lever, alright, I put a 2 mass here, okay, it will weigh the same as if I put a 1 mass here. So that is sort of an established fact. Okay, so if these distances are correct, these two things will compress the spring or expand the spring, in this case the same amount. We get the same exact expansion by placing one or the other in gravity. Now, the same argument could be made that if I put it horizontally and you're looking from above, that this is basically going to measure momentum. You know, that the 2 mass moving half the velocity will have the same effect on the spring of a 1 mass moving twice the velocity. Now, we don't have that experiment. Okay. So, can't say for sure, but I'm just saying, what would the logic be otherwise? If I drop them in gravity. So we do have a version of that experiment where the 2 masses drop from one distance to 1 mass from 2, doubling its velocity. And hitting a hunk of Play-Doh, the result was, you know, they're the same. They weigh the same. They create the same force. So in the most recent junk experiment, in the pile of experiments, is not demonstrating this to be true. Okay, that somehow the momentum, so the spring is got the same compression. You compress the spring the same, you expand it the same amount, and now it's going to go back to its normal state. And you put a 2 mass on, you put a 1 mass on, you don't get anything close to the expectation, which is the lighter thing weighs the same now, but it's twice as far out on the lever. It's going to move twice the velocity in the same motion. So there's no reason for the spring to say this weighs more or this weighs more. The spring can't see that this doesn't, that these two things are different. So that's the simple logic here, that the spring sees the same weight regardless of which one I put on it in gravity. So it's measuring something real. And you're just saying, so, okay, so if I do the experiment and this, you know, goes this distance and this only goes a little bit more, okay, a little more velocity on a pendulum or whatever you want to use, let's just say that's the argument, that's what happens. Well, it has to be diagnosed. Why does that happen? What happened? How did the spring know, or how does anything change in terms of its weight? As I start to push it, how does its weight change? That doesn't make any sense. So the only thing you can come up with really is that the lever does in fact bend, and that bending, when you go further out you get more bending, closer in you get less bending, and that can really be the only excuse for where the energy goes. Why it doesn't get into one object is because the lever's way behind and it never catches up, frankly. It never, because it doesn't keep contact with the object it's pushing, the bend in the lever just continues to exist, and after the object leaves, then it flexes. Okay, and obviously that's not something you can always see, you know, unless you do frame by frame viewing of an experiment. So you did see some bending in his lever, it's just a fact, unfortunately. And so what can you do experimentally to dissect that? So I guess the first argument I would make is that we know the spring can adjust how fast it moves. Okay, how it can give back energy really quick, or it can give back energy really slow. So technically, if I have the 2 mass here, okay, and I move it over here, what should change? From the spring's perspective, it's just saying, okay, it weighs a little more at this location, you know, weight-wise, but theoretically, it still should be able to get the energy into the object. proportional to this distance. So if I put it twice the distance, I should have what expectation for how much I'll degrade the spring's capacity to put the energy in. Now the fact is it can change how fast it moves, or how much it moves. So so I'm just saying, as a test sort of for the lever would just be to find some way to test it where you know what the outcome is going to be. So I'll make sure I know what the outcome should be. Alright, back. So, alright, so we're going to do the simple test. We're going to have the 2 mass here, and then we're just going to move the 2 mass twice the distance. I mean, we should just do it all these distances. What the hell, right? It's not that much. It's not, once you get the setup, it's not that time consuming to move it to all these places and see exactly what you get as a result as you move it further out. Now, I would argue that the spring just has energy in it. That's all it's saying. It has a certain amount of force. It can let the force out quickly, okay, with a high velocity, or it can let the force out slowly, with a low velocity. You can do either one. So when I put the 2 mass out here, it's basically saying, yes, it weighs more, but it's going to take more time to push it. So it will still get it to a velocity, okay, that's going to be the same as this velocity, alright, because the force is in the spring, and the force is just going to go through the lever and say, I really should be able to just apply the force less quickly, so it won't go twice as fast. It'll just go the same speed it went here. So I should get the same result. So putting the object here, 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 any one of these locations, because the spring can adjust, you should be able to test for how fast the spring can actually move. It moves very, very fast here, and the spring releases the energy very slowly here. So this would be a good test, because frankly, you can tell how much you lost by the fact that it really can't go faster here. I mean, it can't go, it's not going to go slower. As I start moving it in, I'm not going to get the same effect, because I'm not competing with another object that is bringing the motion in this very specific. If I drop an object in gravity, it has a very specific velocity. It can't adjust its velocity. It's one velocity, but the spring can adjust its velocity. So the spring can adjust. And so the trick would be, as if this is dramatically slower here, then you know the bending of the lever is what's consuming it. And if it's dramatically not slower here, as you move it in, see, you don't have the problem of a rebound either. Springs aren't going to rebound. Springs aren't going to do any reflecting, The spring isn't banging against it and trying to force something to happen. It's just applying a tension and saying, I'm just going to throw the object. So, so the expectation when it's in closer would be that somehow it's going to go slower. But I'm going to argue that that curve is going to be a pretty flat line. This way going slower is going to be much flatter than this line going faster, and that's going to indicate that bending is an issue, because it's not going to bend much here at all, and so you're going to get all the energy from the spring into the object. That's really the argument, right? We're just arguing, does the spring have a choice? It's almost as if the object is sitting on top of the spring, and you're saying, well, I have to put the energy, the spring has to shoot the energy into the object. It doesn't have a choice. So the spring can do it quickly if it's a light object. It can do it slowly if it's a heavy object. So I can make it lighter or heavier, but I'm going to get all of the force from the spring into the object. So anyway, so that's the experiment to do, is to just move the 2 mass to these different locations and see if you get a dramatic difference in how far it goes. Because technically, the spring should adjust to what the lever has changed. And so in that case, you should get the same outcome. And for the velocity, no matter where you put it on the lever, frankly, I could put the one mass anywhere on the lever. So I guess the thing to do is, for the spring experiment, I mean, I didn't think of this when I was doing it. I should have thought of that. So you're testing two different things. So put the two mass here, and then test with the one mass here. Okay, in the same location. And see if the spring does what you would think springs can do, which is simply just apply the force at a different speed depending on the object it's pushing. So then we start to get into the movement of the lever again, how heavy the lever is, but really shouldn't make any difference. The lever, it has to move. Obviously when it moves the lever quicker, okay, overall quicker, that's got to take more energy out of the system. So now the lever does become an issue, because the quickness that you move the lever changes as I put the mass in different. It's the same speed. Yeah, it has to change. How much the lever, how quickly you're moving the lever is going to change. So the further in I put the one mass, the faster the lever itself has to move, because now this part's moving 4 times as fast, not twice as fast, for this to go twice as fast. So now the weight of the lever will matter, and so that's a new variable. So that has to be understood, that maybe you'll have a 10% difference, because when you're moving the lever quicker, it's going to absorb some percentage of the energy. Now the good thing about the Gosling experiment is masses look like they're much heavier than the lever, like 10 times heavier. So the effect of moving extra lever will be kind of small compared to the weights he's pushing. Alright, so that's an interesting... See, there's lots of variables involved here. But I mean, the bottom line is I wish people would understand, the only way they're going to convince me is they have to come up with an explanation for how the spring knows what these weights are. How does it know? It's measuring a pressure, you know, a pulling pressure or a pushing pressure, and that's all it's measuring. And how can it measure the how can it tell the difference between the two mass out here and the one mass here? Just give me some sort of explanation for how, I mean, the one mass and the two mass. All right. How can it tell the difference? From its perspective, how can it tell the difference? They are weighing the same. How could it possibly know I have to do something different? It's going to want to do the same thing. Alright, so anyway, that's an interesting experiment. So just put the one mass here, and what we'll find out is how much extra the lever will steal a little bit. So you have the expectation that this still won't go twice as fast, because the lever is going to lose a little bit of the, because you moved it faster. But it should be going significantly more than the same speed. So that would be a good test, because it's just more pure. I mean, at least you don't have, you take, see, to get rid of one variable that screws thing up. So if you want to get rid of the idea of bending, then they both have to bend the same amount, right? Both objects have to be encountering the same amount of bending. Well, you can never make the two objects weigh the same, so obviously, you know, the fact is that the further out you go, the more bending you get. So the closer you put it, the less bending. So you can put the one mass, let's just say, if you do the experiment, put the one mass in the same location as the two mass. The expectation would be, okay, that somehow it only goes the same speed as the two mass went. Now it's clearly going to go faster because the spring can do that. And my argument is it's going to go substantially faster. But at least you've gotten rid of the idea that what's stealing the energy from the one mass twice the distance? What's making this only come up half the height it's supposed to be? Well, the only thing that you can really blame is the bending. The only thing I can see that you could bend, that you could blame, is the fact that you wasted energy bending the lever. And that you won't get that back because the object will leave before the bending restores itself. So you lost that energy. I don't see any other possible explanation for the divergence, the difference. So yeah, so you get rid of that as mostly get rid of it. I mean, the 2 mass was going to weigh more, so it's going to cause more bending. So that's the good news, is at least you'll be inverting which one is getting affected by the bending more. But yeah, so what's the expectation? What's the prediction for what happens when you put the 1 mass in the same location as the 2 mass using a spring that can produce, that has a pretty good range in terms of speed. It can go pretty fast in terms of restoring energy. It's not a loose or, his spring looked pretty tight, pretty powerful, so it shouldn't have a problem doubling its speed without any issue. And that's essentially all it has to do, is move this lever twice as fast. And theoretically it should be able to do that. The only loss will be that you've lost another lever's worth of energy. Moving the lever twice as fast will be a disadvantage for the 1 mass. But there shouldn't be much difference. So this really should leave with almost twice the velocity, would be my prediction. 90% of twice the velocity. So put them on the same location and see if you get that 90% number from a spring. Because frankly, the spring can flex. It can produce its force quickly or slowly. You can press it a certain amount, and all I have to do is put a different weight in front of it, and it'll push it at a different speed. That's what springs can do. So, maybe there's some other factor in terms of springs will get sloppier. The faster they're going, you could argue the spring starts to lose energy the faster it has to go. That would be intuitively sensible. So maybe that could be another 5 or 10%. So maybe this number will have to be 85 or 80. I really don't want it to get much lower than that, because then we get close to 60, which is, the 1.4 thing comes up again. Alright, so I think that's a reasonable statement. So if Gosling doesn't mind requests, the request would be just, cut your string and change the weight, and then retie it, reconnect it. Find a place where you can connect and disconnect the string. Put a little hook in it or something, and that way you can change the weight on the single pendulum, one of them, and then you can do the same exact experiment over and over with changing where the weight is, or just changing where it is on the lever, and see how much of a difference it makes when you do the 1 mass and the 2 mass at half the distance, and then do the 1 mass and the 2 mass at twice the distance, and see what kind of results you get. Because frankly, the results should be, there should be a difference. The 2 mass isn't going to do what the 1 mass does out here, and the 1 mass isn't going to do the 2, and you don't have any reflections. There's no place for the energy to go. Okay, in the other experiments, when you collide objects, the reflection can consume a huge amount of the energy, but there's no reflection here with a spring. So you don't have to worry about something bouncing somewhere and stealing part of the energy. So I think it'd be a valid experiment. If you get this 85 number, when you put the 1 mass at the same location as the 2, if you get 85% higher velocity, then I'm going to say win for me. All right. If you get something like only a 40%, okay, win for you. So that's the kind of difference we're looking for. Let's see, it wouldn't be 40, because you have to concede there's a loss to the lever. So, I mean, that's both numbers are going to have to accept that difference. So your number would have to be more like 30. So a 30% increase in the velocity with the lighter object versus an 85% for my prediction. So something like those two numbers. I shouldn't say 30 because frankly physicist Michael says it's 33%. Okay, that's his prediction. So 30 is right on 33, and that wouldn't be accounting for any losses. So we probably should have to drop this down to 25. So if you get below 25, all right, then you can claim, looks like your side, that's a win for your side. We won't call it a victory. We'll just call it a win, a battle win. And if I get this 85%, then I get a battle win. All right, that's probably enough. I mean, I think those are some good points. But I mean, why they don't do this? I mean, they never do any analysis to point out what is going on, how mechanically the system produces what it produces. So again, they just play with this idea that conservation isn't a real thing. Now, the fact that I have no respect for KE as a theory has to do with the fact that it has a crappy history that they won't even talk about, that was premised on silly show experiments. You talk about parallax. Denting clay is, the ultimate kind of smoke and mirrors. Parallax, bullshit, fakery. And that's all this thing's riding on. And again, they haven't overcome all the other stuff that's out there. I mean, the Mythbusters actually did physically crush cars. No evidence of 4 times the crushing, just twice the crushing, twice the velocity, twice the crushing. We don't have anything from the institute that does all those crash tests indicating that shit. Oh well, you can save yourself so much grief by going 3 times slower. You do 9 times less damage. They'd be telling us that if that was the truth. They don't tell us that. And clearly you have no evidence it takes 9 times the fuel to go 3 times as fast, or 16 times the fuel to go 4 times as fast. You haven't addressed any of those arguments at all. It's like they don't exist, and you just keep playing a game with this, little image chicanery. But anyway, let's see if he'll do the experiment. So put the 1 mass at the same location as the 2 mass, and let's see, filming it. Which way to film it? I mean, you got to film it from a little bit better, higher, probably further away to be safer. And it'd be nice to have an overhead view and as many camera angles as possible. Maybe you could just do that. Do the experiment more than once and put the camera above and then put the camera sideways. I mean, come on. But any view is better than no view, and just try it and see what it does. All right.